All right, let's go ahead and get started. I'm Eric Flair. The talk is Observational Science with Python and a Webcam. So I had a webcam, and a couple years ago I made a time lapse. I set it outside on a tripod and took a snapshot every 15 seconds and did a nice little cloud time lapse. It's on YouTube. We're not going to watch it right now because it's kind of clouds. So I wanted to do better. I wanted to make it longer. I wanted to put my webcam in an inside location, so rain or shine, it would take pictures. I wanted to make it automated, so I didn't have to go and just make a snapshot or have it hooked up to a laptop. And I wanted to do it once a minute. And we had a webcam that we had bought a long time ago that had wireless. And we used it when we went on vacation. My kids, my two daughters, had got some pets, some guinea pigs and a rat. And they wanted to make sure that they were okay on vacation. So we set it up. So then that was done. We were done. So I took it. I took it, set it on a second floor window in a little used room. We had an extra bedroom. So I had it pointing west. And then I had a server, and I just, through the wireless, I would pull down a picture once a minute. And there it is, right there. My neighbors, think I'm wacko and spying on them all the time, but it's right here in the, right there in the window. So it's been sitting there for 2 years. So 2 years later, I have about 900,000 image files. That comprises about 11 gigabytes of images. Started at 2:14 p.m. on August 29th, 2010. And I pulled it down for this talk. I pulled down the last images July 25th, which was Wednesday at 4:11 p.m. And it's still going. I mean, this is just where I had to cut it off so I could show you stuff. So the first tenet I'm going to tell you is don't be afraid of big data. I mean, 900,000 image files, that's nothing. You can do a lot of cool stuff when you have a lot of data. So what can we do with all these 900,000 images? Well, one thing we can do is we can do more time lapse, right? I mean, we had a few hours of clouds, but let's do like a time lapse of days or years or whatever. We can use those 900,000 images to explore phenomenon that occurs over long periods of time. Things that occur more than just over a period of one day. We could do a month or a year. We could also take those images and slice and dice them and create unique visualizations. But most of all, with those 900,000 images, we're just going to have lots of fun. So first, we need to organize the data. And what generally do you use to organize data? Database. So how are we going to access the data? Let's use Django. What? Django? Yeah, actually, I'm going to use Django because I'm familiar with the ORM. It's a good ORM. Yeah, it's not SQL Alchemy, but it works for the simple stuff that I'm doing. And my goals for the project were not to learn another ORM. It was just to do some cool stuff with a lot of data. So the ORM works, and it's Django. You can use it for things other than just the web. So the quick setup that I did was, and what you'd want to do if you were going to use Django ORM to load up some images in a database, is you want to create a virtual env. And I use site packages for this because Python imaging library is a pain to compile. You have to have a lot of dependencies, and it's just nicer if your distribution has it already compiled and ready to go. So then you want to install Django. You want to create a project using Django admin start project. You want to edit your settings to point to the database you're going to be using. Create the database. In this case, I'm using Postgres. So I use the create_db command. I create an app called Pix, which is going to kind of store my models for my pictures. And then I sync DB to create those tables in the database. So that brings me to my second tenet, and it's one of my favorite tenets, is don't let small things keep you from your big picture. It doesn't matter if you're using the best or the greatest of ORM, or if you don't write the best code, don't worry about that. Object Relational Manager. It's like a layer on top of the database that allows you to access the database in Python code rather than just type in SQL. So the main thing is, stay focused on your big picture. Don't get too worried about the little things, because the little things will keep you from your big picture. So what do we need to store in our database? Well, obviously we're going to need to store the file location and the file name so that we can access it later. We don't really want to store images in the database. The file system is a good enough database for our images. We want to store the timestamp of the file, when it was taken, and some interesting information about the image. And we'll talk about more what interesting information is. And we also want to flag if it's a valid image or not. Were we able to load this image? It turns out this webcam is a cheap webcam, and it sometimes didn't return valid JPEG images. So here's our model, and I don't want to spend too much time on it. I just want to show you that this model encapsulates just exactly what I said. Right there is the file location and the name. There, I'm putting an image timestamp in the database. And I also add hour and minute. And the reason I did that is just because some of the stuff I wanted to do is it made it really easy to create the queries for hour and minute if I pulled it out of the timestamp and saved it as a separate column. Here's some interesting image data. And I was using PIL, and PIL has some interesting statistics that you can use off the image. The first is I took the very center pixel of the image and saved it specifically. Also the mean and median colors, and also the standard deviation of the color, the RGB components, and also the min and max colors. And then finally, I had a valid. It's a Boolean field. And then in Django ORM, in the model, I can choose a default ordering. For most of my stuff, I want a timestamp ordering. If I want to change that, I can. But if I don't specify, I don't have to specify, I want this in timestamp order. I want this in time order. So I put ordering timestamp so that it automatically does that for me. So now we're going to load the data. We basically are going to do 4 things. We want to iterate through a directory of images. We want to parse the file name because the file name has the timestamp of when it was taken. There's no EXIF data or anything like that on the image itself with this webcam. So we parse the file name, get the timestamp. We also pull out the file timestamp to compare because, just in case we wanted to see if there was some cases where the file got pulled and saved, but then something happened or whatever. And then we want to load the image itself to collect the statistical information like the center pixel, the average in color, and the median color. So really, this is all we need to do. Python makes it really easy. This is our directory walk. os.walk will walk through iteratively a set of directories given a given directory. And fnmatch will allow us to filter our files that come back from each directory to match a specific template. In this case, if it turns out that there's other junk in those directories, I don't want to pretend that they're files and try and load them. I know that all my images are named image dash a timestamp .jpg. So I just iterate through each of those. And that should be indented. When I copied and pasted, something happened. But this is within the for loop. So I pull out the timestamp out of the file. I know it's between a dash and the dot, so I pull that out. And I turn it into an integer. I want to save it as UTC. I don't know if anyone hit Tavistock yesterday, but you want to save it in UTC as a database. It makes a lot of things easier. And then as I'm loading each image, I want to open up the image. So this is the part right here where I load the image. I do it in a try except block because if any part of this loading of the image fails, I know it's not a valid image file. And I do have not valid image files. So with Python imaging library, it's very easy. I just have to do image.open. I pass it the file path that I've gotten already. And then there's some methods on the image where I can get the pixel. In this case, the first box is getting the center pixel that we talked about before, the very center pixel in the image. And the size, if it's not 640 by 480, whoops, I was a little too, if it's not 640 by 480, then I want to declare it invalid. 640 by 480 is what the webcam produces. And then there's a statistics module in Python Imaging Library that if I pass it an image object, I can get some statistical information on it. And the two that I'm using is stats.mean and stats.median. Mean is the mean color, and it's the average RGB components. And median is if you order the colors in the image, it takes the one right in the middle. And so you know with median, you're actually getting an actual color that's in the image, whereas mean, you'll get, you know, an average of each of the RGB components. All right, so it took about an hour or two. I just ran it in 6 threads. I gave it specific directory parts. I store it actually on my server, the first 4 digits of the Unix timestamp, and so each directory has that. So I kind of pulled out those directories, ran it on 6 threads. It only took an hour or two to actually do all that. So to iterate through 900,000 images, you know, load them into memory and do the statistics on them and save it in the database. So it only took an hour or two. It wasn't bad at all. So that brings me to my third tenet, is you have a 1990s supercomputer on your lap or under your desk. You know, one of the greatest crimes, I think, in technology today is the underutilization of CPU cycles. You know, I mean, how much CPU do you really need to look at Facebook or Twitter? Honestly, you know, there is so much computing power that just is wasted, and it's such a crime. So use it. You know, do some cool stuff. You know, run some things that take hours or days to run. So let's explore our data now that we have it in the database. Obviously, having it in a database makes exploration very easy. So this is actually just pulling stuff out using SQL, which is, you know, the language to query the database. In this case, what I did was I found the image that had the largest size. In JPEG, you know, the greater the size, the less it was able to compress. And if it's harder, if it was not able to compress as much, then that means that there was more complexity in the image. So this was the image that had the greatest size out of those 900,000. As you can see, there's quite a lot of complexity in that image. The next thing I did was look at which picture had the greatest overall standard deviation. I just added up the standard deviation from the red, green, and blue components. And as you can see, there's white where the sun is starting to peek out from the clouds, and there's dark where the cloud shadow is still on most of the area. There's some really nice blues in it. It's a very pretty picture, but that is the picture that had the greatest standard deviation of the red, green, and blue components. And as you can see on the timestamp, that was at September 29th, 2011 at 5:20 p.m. And as you can see, the -4, my desktop computer is at Eastern time, so it was able to convert automatically that UTC timestamp that I've saved in the database as the local time. All right. So as you know, those were just pulling out individual images. Let's get some specific information about the data set as a whole. The first query just looks at the min and max timestamp, so I know that's where I pulled out from an earlier slide, you know, when I started and when I finished in the database. The next query looks at the number of images in the database, and then I look at the number of images that are flagged as invalid. And finally, the third query looks at an image that is invalid and has the greatest size. So I just wanted to kind of see what it looked like. As you can see here, the gray at the bottom of the image, that's where the image stopped loading, you know, from the webcam. Some programs will not open this JPEG because it was really technically not a valid JPEG. It actually was able to, LibreOffice was able to pull it in, but the GNOME picture viewer won't load that. So that's an example of an invalid image. So, you know, what do we What do we know? I mean, yeah, this data sucks. I mean, 30,000 invalid images out of those 900,000. I mean, that's 3.3% of all my images are invalid in some way. And worse yet, there's not a file every minute. There were times when my cron job failed or my server was down or the power went out, where I don't have images. If you actually look at the number of minutes between my start and end times in the database, I should have over 1 million images. So we're missing over 10% of all minutes within that time period. That sucks. It's even worse than that. I didn't bolt down the webcam. Yes, this room is not used very often, but it is used, and it gets bumped. It's sitting on a windowsill. It gets bumped. As you can see, the first image was where we started. We were there for a while, which was kind of scooted over to the right. And then look at that one. That's like looking up like this. It must have fallen or something. So we don't even have necessarily a lot of consistency on its pointing. Thankfully, it's not used that much, and we have enough that it's OK. All is not lost. Actually, as I was putting together the previous slide, I was actually listening to OK Go's All Is Not Lost song from the Humble music bundle that came out. So it was serendipity, so I had to put that slide in. All is not lost. You know what? Yes, the data sucks, but you know what? We can still use it. We can still make some really cool things from it. So, and that brings me to my fourth tenet. Real-world data is messy, and that's OK. We just work around it. It could be good enough, right? Nothing in life is perfect. Your code's not perfect. Your data's not perfect. But it still seems to be OK. So how are we going to work around it? There's three main things that in this talk that I do to work around this data. The first is to kind of normalize the minutes. If we're going to make a time lapse, we don't want it to like jump ahead an hour because there was no images for that hour. That kind of doesn't show the constant progression of time. So if we put a table and put all the minutes in them and then associate them with an image, then at least if we're doing time lapses and things like that, we have a constant time. And so when we have a minute that doesn't have an image associated with it, we can also then accept images that are near the missing minute. In a time lapse or something like that, it'll pause for a second. It'll look like your video is stuttering, but it's not. It's just that we don't have a minute there. Another thing we can do is when we can't find an acceptable proxy, the sky 1 minute later is going to look similar to the sky, a minute before. But in some cases, we were way off. We were, power goes out for 5 hours. It's in the middle of that 5 hours, we're not going to find an acceptable image. And in that case, we just put like a gray picture or no image or whatever. So there's lots of things we can do. So first off, let's make time-lapse movies. Just regular old basic time-lapse movies. So there's going to be 4 things we're going to do. We collect a set of images in frame order. We pass those images to a movie maker to compose them from single still images into a movie. We wait for the movie to be made, and then we watch the movie. It's very simple. And this is the Python code that does it. I mean, it's not a lot of Python code. All right. So the main thing is to get our set of images. This is using the Django ORM. We're using filter to filter between a start and an end time. In this case, we are starting at midnight on April 7th, 2011. As you can see, we're using time delta, days equals 1, to add 1 to that start time. So it's midnight to midnight. Again, we're choosing midnight to midnight Eastern time. So see where TZ info equals ETTZ. The line above that, you can see I'm using the time zone PYTZ to set the time zone to Eastern. So I know I'm midnight to midnight at the local time of the webcam. So now I have my set of images returned in an array. And image sequence is a class that I created. Basically, you pass it in an image, and it adds it to a list, and then it'll pass it out to mencoder, because mencoder accepts a file list. And so basically right here, I'm just iterating through each picture that was returned from the database, passing in to my image sequence object the path to my image. And as you can see, if the picture is not none means I have a valid picture. I'm using the normalized table, so there's going to be minutes that are not going to be pointing to a picture because I couldn't find a nearby picture or whatever. So in those cases, I'm going to display my no image image, which is basically gray with no image. Okay, piece of cake. And then on my image sequence object, I have a method called make time lapse. I give it a file name and a number of frames a second that I want, and it calls out the mencoder to do that. And here's that right there. So this is my entire image sequence class. You can see there's actually a couple of additional helper methods. I can actually pass in a list of images or whatnot. But basically what it does is make time lapse, creates a named temporary file. Again, Python makes it very easy to just throw out a file that I don't care about. It'll clean it up when it's done. So I create a named temporary file. I write the images in the sequence that I want them in the movie. I set, this here is all options to mencoder that I kind of, found on the internet and stuff. Defaults work fine, but I was just kind of playing with different things to see. As you can see, the mf:// line, that is mencoder format. You can send in a list of images in a text file, and that's what I do instead of having to pass them all on the command line. And then that creates a MP4 movie file. I just do subprocess.call to call out to mencoder from the command line. So Python, that's how you call out an external program. You don't always have to use Python. Mencoder is great. It calls out to mencoder is actually a layer above like FFmpeg, for example. So it makes it easier to do things than FFmpeg. So, all right. So let's watch this movie here. Here is our time lapse. It starts out at night. It's midnight to midnight. The cool thing about this particular day is you'll be able to see like gravity waves. And gravity waves are where you have an atmospheric condition where you have a wide variation in temperature. So you have warm air below and really cold air at the top. And the warm air is not dense enough to support the cold air. So the cold air starts going down, the warm air starts rising because warm air is less dense. And what happens is you have this kind of back and forth, almost like waves. And you'll see it really good here for a brief period of time, but you can kind of see how it's kind of dark and light. Those are gravity waves, and it's the atmosphere just rising and falling. And it's on YouTube. You'll probably be able to see it better on your own monitor. But that right there is something you can use to show an atmospheric phenomenon. All right. So now we're not just limited to consecutive minutes. Those are your classic time lapses, right? It's showing something speeded up. But we can do better than that. Why don't we make a movie of a specific time of day? We got 2 years, so we can make a 700-frame movie of a specific time of day. In this case, I'm choosing 2200 hours UTC, which is near sunset for most of the year. And so what I do is I filter out, using my hour and minute columns, to filter out getting me the image at 2200 hours UTC every day in time order. So the first frame of the movie will be 2200 UTC, January 1st. Then the next frame will be January 2nd at 2200 UTC, and then so on. So this is getting familiar. Once I get the list of images from the database, I iterate through them, pass them into my image sequence class, and then I make the movie. So let's watch this movie. So it looks like the sun is setting, but this is taking consecutive, one image a day. And what this is really illustrating is how the day shortens and lengthens. As the sun is going down, that means there's less daylight because at the same time of day, the sun is lower in the sky. And then as it's going up, that means we're heading towards summer. The day is lengthening. And there's where the camera moved. But that's okay. We can still see what's happening. You know, the sun is going down. It looks like it's setting. But really, that's just the same time of day. Every day, it gets darker. You know, like when you come home at night at 5 o'clock in the wintertime and it's dark already. Well, you know, but then it's 9 o'clock in the summertime. So that's what this is illustrating. And we were able to easily show this by, you know, by pulling together our images in such a manner. And then I did this purposely. I put no image as the last one so you can see, you know, if it's just so happened I didn't have an image, it would show no image. All right. So we can do better than that. Now, what if we want the sun at the same height in each image, right? I mean, obviously, we can't just look at the day itself or the time itself. We need to have some sort of way to say, okay, I want the sun in the same position in the sky. I don't want to manually go through and find, okay, yeah, that one looks about right. How are we going to do it? Any guesses? Well, we can anchor on sunset. We know that if we can determine when the sun is setting, we can say, okay, a specific time before sunset, it's going to be the same height because the sun, you know, moves. Obviously, the Earth doesn't change its speed of rotation. So we can say, okay, let's say an hour before sunset, you know, I want to take that picture an hour before sunset. But that time of sunset changes every day. So this is where I thank Brandon Rhodes. He created the PyFM library, which is based on a C library that allows me to very easily calculate sunrise and sunset. And that actually is Brandon, and his cat licking him. So I didn't lick him to thank him, but all right. So I created a kind of a layer on top of PyFM to make it really easy. Obs equals sky.webcam basically already pre-populates an observer with my latitude, longitude, and elevation and things like that. And then sky.sunset, if I pass in my observer's location and the time that I want, it will find the next sunset. So sky.sunset will return the time of the next sunset given the time that I passed in. And then you can see I do minus date time, time delta, minutes equals 70. So I want to get the time 70 minutes before sunset. So I can't use filter. I can't get a whole list of things from the database. I have to get each individual frame. So you can see I don't have it highlighted, but normalized picture.objects.get, I get the image at that time. So then, once I have that normalized image, I'm doing a little bit more in this one. In this one, I'm saying, you know, this is where I'm saying I can play with bad data. If I don't have an image, if there's not an image on that specific minute that I've selected, I grab a set of images from 20 minutes before to 20 minutes after, and I pick the first one that's valid. And then if that doesn't work, then I say, okay, I'm going to go ahead and use yesterday's image at that time that I used yesterday, because you know it's going to be pretty close, right? It's going to be close enough to illustrate our purposes. I don't want to have it flashing in and out, you know, no image, no image, no image. So it's good enough, right? If that doesn't work, if I don't have an image from yesterday, then okay, then I'll display no image. So here's my little layer on top of PyFM. You know, FM has objects for the sun and the moon, and then if you look at my observer function, I created an observer with a specific latitude and longitude and an elevation, and that's exactly where the webcam was located. And then if you look at sunset, I changed the time that's passed into UTC in case it wasn't UTC already, because that's what PyFM takes. And then I say, okay, give me the next setting of the sun object, and I basically return it in Eastern Standard Time. Now you can see I also have moon set and sunrise. You know, there's a bunch of different things. I can do things. There's a lot of different astronomical objects in PyFM, Venus, Jupiter, you know, all the planets, of course, and different things. So I can actually use the basically same template for all the astronomical objects, but I'm only looking at the sun and the moon right now. So now let's watch this movie. So you can see the sun just moving off to the left. And then it's moving off to the right. It doesn't stay in the same spot in the sky at all. And this is very vividly illustrates, how the sun moves. I mean, I sit in my basement all day. I never look at the sun, but you can see, it doesn't set in the same spot in the sky. And I think, as a society now, we focused on our computers and whatnot. We don't really sit out a lot and observe how the sky changes over seasons and years. So you can see it now. It's marching back to the right, and there you go. So pretty cool. There's two stills from the movie, and you can see, the webcam didn't move in this case. The silhouette's still the same, but you can see just in 2 months, and also you can see, the time that the picture was taken, 7 p.m. versus 5 p.m. So the time is getting shorter, and the sun is moving throughout the sky. The Native Americans, the Mayans, they all knew that. Chichen Itza, at the equinoxes, I believe, you see that little shadow. It looks like kind of like a wavy thing on the stairs. It's aligned such that on those 2 days and a couple days before and after, it creates this shadow. And at the bottom of that stair step where that shadow is a serpent's head, so that it looks like a serpent. Here, this is Chaco Canyon I think it's New Mexico, where there's a slit in the rocks, and this is like a circle in concentric circles, and on the equinoxes, it's right in the center of the circle, and then it progresses, and they use that to track time. So our fifth tenet is once you have a foundation, we're using PyFM, we're using a database, we're using all this stuff. It doesn't matter how messy our data or code is. We can just keep building higher. So we're going to build a little higher. All right, so we can also take pictures at night, right? It's 24 hours. So did I capture anything interesting in my nighttime pictures? Most of the pictures are almost black, right? But maybe there's sometimes we catch something really cool. So what is the definition of something interesting at night, right? It's something that's bright, right? Brightness is a proxy for interesting at night. Because if it's not bright, we're not going to see it. So we're gonna look at brightness of the images, and we're going to make that very easy to identify interesting things. And because it's easier to spot black spots on a white background than the reverse, astronomers know this is how they look for like how Pluto was found, for example. We invert the images. So what we're going to do is we're going to process each image that's at night. We're going to stack all the images from that one night into a single all-night image. So we don't have to look at individual frames. We just kind of stack it, and wherever it's black, we know that something interesting happened. And we're going to take it from 1 hour after sunset to 1 hour before sunset, because those are our black times, where it's dark. And because we've inverted the images, black splotches are our interesting things. So again, this is starting to look very familiar. Instead of start time being sunrise to sunset, we're going to take sunset to sunrise the following day. We pass it into our image. For each image in the picture, we're going to do some processing. We didn't do any processing on any other ones. Python imaging library allows us to grayscale it. So we're going to grayscale it. So we're going to convert RGB to 0 to 255. And then we're going to invert it. So 255 is going to end up being black, and 0 is going to end up being white. All right, so, and here, we're going to threshold it. So it's either going to be all black or all white, right? Because if we stack images that are almost white, it's like looking through a whole bunch of dirty windows. It's going to eventually look black, and then it's not going to give us any information. So we've decided anything that is almost white to white is going to be white, but anything that has any little bit of brightness, we're going to consider interesting. And 224 is what I found was a good number. Finally, we're going to draw that image, and we're going to put it into our stacked frame. So we have our image that we've done some processing on, and we have another image that we've created, and we're going to stack that image. And there's a thing called multiply. with Python imaging library. And basically, multiply means if something is black and you multiply it with white, it stays black. If something is white and you multiply by white, it stays white. So basically, it's almost like you're stacking all the interesting pieces for that, for all those images. And this is what it looks like. This was actually a famous. I don't know if you remember February 26th when there was the conjunction of the Moon, Venus, and Jupiter. Those are the 3 astronomical objects that my webcam is able to detect. This is the Moon, this is Jupiter, and this is Venus. So you can see them tracking in the sky as they set. The little blotches on the bottom are ground objects, lights, people's lights turned on. Okay. So this was one of the ones that came up. Wow, that looks kind of cool. What is that? Well, it's actually lightning. It lit up the clouds, and I actually captured it. I mean, this takes 1 picture a minute, and it actually was able to catch lightning. There's actually another case where it caught lightning, but that's actually lightning. So that is interesting. Is there anything more interesting? Wow, look at that. This was October 16th, 2010. There was an image of almost the size of the moon. You can see the moon track, and you can see the track of Venus. So it's not either of those. It showed up in one single image. It has a little hooked tail here. I don't know what it is. It showed up 3 weeks later. So I don't know. Now here's my last oddity. This was the biggest weirdness right here. There's the moon on the left-hand side. Right there is an object. It was circular. It had a very green tint around it. It looked like that. So in the same night, there's the moon. It was a crescent moon. And this is all blown up to the same scale. There's the thing that we found. And again, it was a single image. It was really bright. It was brighter than the moon. So either it had the size of the full moon, or it was so bright that it saturated adjoining pixels. I have no idea what it was. It could be, a spotlight of a helicopter or something. I don't know. I mean, there's a couple times where I've caught airplanes, but they're very, very, they're more like, Jupiter than they are the full moon. So now let's make some art, okay? We've looked at whole images so far. Instead of using the whole image, let's use one single line from each image. Kind of like a scanner. You know how a scanner works? You put a piece of paper down, and it goes, it's scanning one line at a time. So we're going to start at midnight, and we're going to scan, stacking lines like this. This is the result. We take each image of the day, and we scan, and we take one line from that image, and we just kind of stack them lower and lower. There are 1,440 minutes in a day, so that means we're going to be 1,440 pixels high, and we know where we're at by we say, okay, how many minutes into the day will be your Y value. So this is starting to look from around. I'm not going to spend a lot of time. We filter our objects. We get 1 day of objects, and instead of putting them into a movie file, what we're going to do is we're going to create an image. And we crop the image. This crop, again, with Python imaging library, instead of pulling each individual pixel and painting it on our resulting image, it's so much faster to just say, okay, give me an image of just cropped to just that one line, and I paste it into my resulting image, starting at 0x, and I want it down the picture y, which is the number of minutes that it is into the day. So here's an example right there. Midnight is at the top. That little blotch right there is the moon crossing our scan line. Then we have sunrise. You can see where it's gray is cloudy, less cloudy is blue. We can see where the sun crossed our scan line, and sunset. It's kind of pretty. Lots of blues and grays. Here's a really cool example. This is on the left is the shortest day of the year. On the right is the longest day of the year. You can see how different, how much more daylight there is in the summertime than there is in the winter. You can see that the December day was gray almost all the day. The grayness in the afternoon is partly for a couple reasons. One, it does tend to get more gray in the evening because of the temperature and the particulates and stuff. Also, my window's a little dirty, so it kind of reflects a little bit. But anyway, you can kind of see the blue. It certainly was very clear in the morning. All right, so my sixth tenet is don't be afraid to be creative. Science can be beautiful. I think those images are really cool. So everything we've done so far has spanned a day or less. You know, I mean, what if, you know, okay, so you know, we viewed full images of interest. We've taken full images and made them into movies. We've stacked full images to find UFOs, and we've took a full line of one full line from a day's worth of images. But everything that we've done is just a day or less. Let's use all the days. What if, instead of an image row being a single minute, like with our day strips, it was a whole day? So each pixel in the row was 1 minute in the day. And then each of our 900,000 images would comprise a single pixel in our Uber image. So here's a visual representation. Along the x-axis, we'll have midnight to midnight for a single day, and then each row in the picture will be a whole day. So each pixel in that row represents 1 minute or one webcam image. So we basically get all the objects in the database, all 900,000 of them. We create a new image that's 1,440 pixels wide by however many days we have in the database tall. And we iterate through every single picture. We change the time zone to Eastern time because we want it to be midnight to midnight. And so that gets our X and Y. And then we basically paint that pixel. And we're using median color, which was from our image statistics. So we're going to get the middle color of the image. And then we save it. And this is the result. That comprises 2 years. You can see very visually there how the days get shorter, how they get longer. If you really, if you look at it at full resolution, you can see that there's an asymmetry. You know, the longest day of the year, or I'm sorry, the latest sunset does not correspond with the earliest sunrise. And I don't want to go into it right now because I don't have a lot of time. But you know, that could be the launching point of a whole discussion of exactly how, you know, how things move in, you know, how the Earth orbits the sun, how it's tilted, how, you know, how it's closer to the sun in the wintertime and farther away, and that's how some of that asymmetry and all that. You can see where it's kind of gray is more cloudy, blue is less cloudy. And, you know, this is just plotting Eastern Standard Time. I'm not going into daylight savings time, but you can also use this image to talk about what does daylight savings time really do. And here's what it does: is it shifts the time in the morning in the summer later to normalize sunrise time. So the whole, you know, they ask where does the savings come in daylight savings, right? What are you saving? I mean, there really is. You're not changing the length of the day. You're not changing the length of the sun. What it's doing is it's like, okay, you wake up at the same time every day of the year, right? Well, there's less daylight that's already passed when you wake up in the summertime, right? You know, it shifts in the summertime, which is right here. It shifts that forward so that when you're waking up, you still have lots and lots of time in the day. And that's for the farmers, right? You know, the expense, what you lose then is you have a wider variation in the sunset time, right? That's why in the summertime it's 10 o'clock and it's still light out. And in the wintertime you're driving home at 5 and it's dark, right? You know, so that's what you lose. But there is no time, there is no sunlight gained or lost when you save time, or but again, this image very visually shows exactly what happens with daylight savings time. Yes. Mm-hmm. Those two bars are times where I had large periods of time without webcam images. One was, I don't know if you remember the derecho that went through, we lost power. Well, that's one of them, and I forgot that something happened when power was regained. I had to reset the webcam. And so that was part of my processing to kind of say, okay, I'm going to find some cool things so I don't have a black bar. So it kind of at a high level you can kind of see what's going on. So that's what it was. It's an artifact of choosing images. So in conclusion, Python makes it easy to answer the question, what if? So that takes me to my 7th and last tenet, is don't be afraid to ask what if, and don't be afraid of where it takes you. This is where all my, and actually before I talk about that, some of the what if questions, that I haven't answered that I could add to this is, what if I linked temperature or wind speed, like from a weather station to those images, and then say on the day strip I plotted temperature with respect to the time. What would that show me? Would it show me that temperature tends to rise at certain periods of time and fall at others? What if I looked at the color in the image and used that to help determine how much cloudiness there is or not is? What if I had a better webcam that instead of 640 by 480 it was full HD? What if I had a webcam that had better exposure time? What if I pointed out a window that actually was clean? There's all kinds of things, what ifs I could do and get from there. All this talk is available. You can certainly pull it down. The code, I dumped it. Obviously it's not in a real good shape, but it's all available. You can kind of look at what I've done. And eventually, this right now is just a coming soon page, but in case Bitly ever goes under or whatever, I want to put all this stuff on my website, so you'll have links and maybe some additional discussion as well. So that's it. Thank you. Sorry, okay. So we just have time for maybe one question. Pete? Python 2, 2.7. You have to get it. Yep, it's not included. PyTZ is also not included. PyFM is not included. Django is not included. But they're all easy to get. I use pip to pull them down. I guess that was short. One more question, real quick. Yeah. No, but that'd be great. Yeah, yeah. And I could also use OpenCV to look at motion tracking of the clouds to see how their velocity and stuff like that. Yeah, yeah. So, but yeah, that's great. But actually, you had one before.
Are you afraid of the consequences?
I hope everyone takes it in the proper context. Yeah. Well, I mean, here's the thing. Everything's a UFO until it's not, right? Until you've identified it. That's why you hardly ever see clear images of aliens and UFOs landed, because once it becomes clear enough that you see that, you realize it's just the Goodyear blimp, or that's why they're always so grainy. It's I don't know what it is, so it is truly a UFO. I didn't say it was an alien. It truly is unidentified. I don't know what it is. It most likely is an aircraft, or it could be a meteor or something. Who knows? But it most likely is not aliens. But I don't know 100%. So one real quick. I hadn't thought about that, but I think what you should do is, webcams are really cheap. I think you should point a webcam out your window, take a picture every minute, and do your own processing. Do it. I mean, the more the better, right? I mean, but certainly if anybody wants it, I can, it's 10 gigabytes. If you give me a big enough USB stick, in a couple days it'll download onto the USB stick, and I'll give it to you. Anything else? Yes. Mm-hmm. Yeah, the pan and tilt, that's a decent idea. You could actually see then when it moved and kind of move it back and stuff. No, I haven't, but that's a great idea. I mean, that is a great idea. Another idea I had was having a full 360, and mounting it on my roof, and whatever. I think we probably have time for one more. I hadn't thought about that, but yeah, I could. I would. Yes, absolutely. I would be open to that. I'm not an artist, so I don't know what that means. But I would. Yeah, I think that would be cool. I think that'd be really cool because it really, it's beautiful. It's neat to look at, but it also illustrates, concepts of the way the world works, and the way the universe works that we don't often think about because we're inside all the time now.
If you pitch this to make magazine, it seems like something they would publish.
No. Okay. I will. Thanks. All right. Thank you, guys.